So welcome back. We are starting the second lecture of the series by Matt Hogancamp.
Cool. All right. Welcome back, everyone. Thanks for sticking around. Okay, so lecture 2. So, I want to start by sketching the definition of Kavan-Ruzensky homology, and then we will discuss this homological perturbation lemma and how to basically how to streamline computations. So what we should be able to get to is we'll compute some invariance of knots like two-strand torus knots. Why are they not today? Okay, so here is a lightning fast, or as close to that as I can approximate, introduction to Kavan-Ruzensky homology. So we're going to fix an integer n and define a ring. So Kavan-Ruzensky homology. Okay, let me just make some definitions. Sorry. So let K be a fixed field, or it doesn't actually even need to be a field. It could be any commutative ring. So everything here actually works over the integers if you want. So R will denote this polymer ring in just n variables. We'll make this a graded ring by declaring that the x's have degree 2. And because we have 3 gradings around, let me emphasize, they have q degree 2, a degree 0, and t degree 0, by writing it in this way. So what we're going to do is we're going to sort of first define some complex, some chain complexes of bimodules associated to the elementary braid generators, the Artin generators, and the inverse. So these are going to be some explicit complexes of bimodules. So they'll be complexes of, in fact, graded bimodules. R is a graded ring, and these will be complexes of graded bimodules over R. I'll tell you how to define those momentarily, and then censoring these things together. We'll define a chain complex for any braid or any word in these basic generators, so any braid or braid word. So any braid on n strands. And then thirdly, there's going to be an operation that takes a complex of bimodules and produces a complex of vector spaces called Hochschild homology. So Hochschild. And by combining all 3 of these things, this is going to be our definition. So taking Hochschild cohomology of that complex, this is what will produce the thing that a moment ago was called C of beta. Okay, so this is the rough outline of how you define this complex. So, but it all boils down to just the complexes that we associate to the positive and negative crossings. Okay, so definition. So I'm going to let bi, so for I an index between 1 and n minus 1, I'm going to let bi be the bimodule over R, which is, so I'm going to take R tensor R, so I have a left action of R and a right action of R, and then I'll quotient out by a relation that tells me any symmetric polynomial in xi and xi plus 1 can be slid from the left side to the right side. So I'll write that this way. So we're tensoring over, we're not tensoring over K, we're tensoring over this guy R Si, where R Si is a subalgebra of R consisting of those polynomials which are invariant under swapping xi and xi plus 1. So basically what we're... Yes?
These are the number of strands?
Huh?
How should we think about n?
N is the number of strands of the braid.
Okay.
So you should imagine, so n here is the number of strands. Some of you either have or will see pictures of webs in the context of link homology, and the picture associated to these bimodules, bi, so is a sort of, this is the picture that we associate to the bimodule bi. If this picture makes sense, then awesome. If it doesn't, then ignore it, okay? I don't want to explain it. And if I'm being truly honest with myself, there's actually a grading shift, Q inverse. So that the element 1, tensor 1, now lives in Q degree negative 1. Who cares? Okay. And so tensoring over RSI, what that means is, for example, this polynomial, which is obviously symmetric with respect to exchanging xi and xi plus 1, on the left factor, inside this bimodule, it's equal to the same thing on the right, and similarly okay, so that's bi, and out of bi we will construct a pair of complexes. Sorry, I'm gonna erase this real quick. Sorry. Definition. So again, for I in the range 1 to n minus 1, we'll define the complex f sub I to be, so it'll be a two-term complex. So in degree 0, I'll put a bi, and then in degree, so because we're going to have 3 gradings floating around, I think it's really important to keep track of all of the gradings explicitly. So I'm going to write it in this way. So this notation means that we place R in cohomological degree 1. So that the T, remember T here denotes the sort of cohomological grading, and placing a T means like we're shifting that R by 1 in the cohomological direction, and then by negative 1 in the Q direction. So Fi is just this two-term complex and then zeros everywhere else, where the map is there's a unique bimodule map from BI into R, the identity bimodule. There's a unique map sending one tensor 1 to just 1. Okay? And because of this shift that I sort of introduced after the fact, that map is not going to land inside R, it's going to land inside R with this Q shift.
I have another question. So
Yes?
you wrote VI equals to R tensor R, and this RSI is a part of this entity, or it is like on the side? Is R to SI below?
This RSI is the thing that you are tensoring over, so which means you allow anything which is in here. So this guy is a subalgebra of R, it's a subalgebra of this guy, and it's a subalgebra of this guy. And we are identifying those two subalgebras. So we are allowing anything which is in RSI to slide from one side of the tensor product to the other side of the tensor product.
Okay.
So basically, we're saying that, so usually tensor products you think of as being the sorts of things that represent bilinear maps. And this guy represents being bilinear relative to this anyway, maybe I've said too much. But yeah, so this means we're tensoring R with R over this RSI. At the risk of saying
Maybe in those formulas over there that you wrote, it would help to call the other guys Y, the other copy.
Yeah, exactly. So thank you. I actually I was just about to do something similar. So our tensor R is so R is a polymerring in variables x1 up to xn, but now we have two copies of this. So we can identify it with, and instead of using the letter Y, I'll use the letter x prime. So we have x1 up to xn, which are the left. That's the left factor, and then we'll also have x1 prime up to xn prime. That is the right factor. And then what we're saying is that BI is, well, you take your alphabet of x's and your alphabet of x primes, and then you mod out by these relations. So you mod out by xi plus xi prime.
Okay, it's easier this way, yes.
Yeah, it's easier this way. I agree. Okay, cool. And then the map in that language is just there's a quotient. R itself, the trivial bimodule, is thought of as the quotient in a similar way. You could think of this as being the quotient where you take the alphabet of x variables and the alphabet of x prime variables, and then you mod out by, well, xi equals xi prime for all I. So you just identify every xi with every xi prime. And so you have, you can see that R is itself a quotient of BI, and that's this quotient map. So that's what we do here. For Fi inverse, we want to imagine like taking the dual. So now the R is on the other side, and instead of it being in cohomological degree 1, it's in cohomological degree -1. So the shifts get inverted. And now we need a map from R to BI. And we cannot send 1 to 1, because that will break the relations that we have. Because xi is equal to xi prime here, but it is not equal to over here. So what we do instead is we send 1 to, and I'll use this x prime notation. We send 1 to xi minus xi plus 1 prime. And there's a really pretty argument for like why this is actually a bimodule map. It's like pretty elementary, but I think it's worth saying because it's a little fun. So this is well defined. So the claim is that this element right here, in order for this to be a valid bimodule map, we must show that this map kind of respects the relations that define R. So anything that was 0 inside R had better be 0 inside the image over here. So in particular, xi minus xi prime in here is 0, and we need to show that it maps to 0 over here. So we need to show that this guy is killed by multiplication by xi minus xi prime. We need to show that this is 0. Why is it 0? And this is fun. Well, because notice, this expression is symmetric in xi plus 1 prime and xi prime. This is symmetric, is invariant with respect to exchanging xi prime and xi plus 1 prime, because exchanging xi plus 1 prime and xi prime just switches the two factors. So what that means is that because it's symmetric with respect to xi prime and xi plus 1 prime, that means I can remove the primes. Anything that is symmetric in the primes is also equal to the same thing where you remove the primes. So this is equal to okay, this is a little silly. Of course, you could just expand. I mean, anyway, this is a valid argument. Xi minus xi is 0, so okay. So that's why this is a valid bimodule map. And furthermore, it's grading preserving, if you think about it, because 1 has degree 0, but then we bump it up to a degree 1 element by multiplying by q. And this guy has degree 2, but is being bumped down by 1 because of the shift occurring in bi. So you can think about it for a second and verify that this really is a q degree preserving map. And these are our...
Quick question. I understood what this claim, why it's 0, but I didn't get the last step, which maybe you considered obvious. How this claim implies that it is a good map. So what do we want of it that we use the claim for?
Do you agree that this is a bimodule map? The claim is only telling us that this is a bimodule map. So actually, what we need to show is we need to show that this element is annihilated by xj minus xj prime for all j. Because those elements are exactly the things that define R as a quotient. So we need to show that this is 0 for all j's. But it is it's only interesting for when j is I or I plus 1. If j is neither I, so if j is not I and not I plus 1, then this element is 0 because this expression is symmetric in xi and xi plus 1 if j is not either of those indices. So this thing is already 0 inside bi. Okay, so So this relation is true. And then in the case when j is I, that's what we proved above. In the case when j is I plus 1, the proof is very similar.
Okay.
So this is telling us that this is a bimodule map, so we can form this complex. What you want of this complex is not just that it exists, but that it gives us an invariance of braids. So the theorem that I will state, but not prove unless people really want it. No, okay, it would be too much to prove it. Let me just say, it would be too much to prove it right now. But the theorem is that these complexes satisfy the braid relations. So first off, if you tensor these, so these are both complexes of bimodules. And maybe I'm glossing over this too much. Let me take just one step back. So if we have, so given bimodules, I'll just call them B, let's say, and B prime. And then I'll write the subscript. So if B is a bimodule, it has a left action of R and a right action of R, and B prime is also a bimodule, then you can tensor them over R. This is just like so I mean it's the sort of typical thing one does in algebra, which is you just kind of tensor them over the field, and then you make a further quotient where you identify so you identify you sort of you mod out by the relation, which is anything on the right of a B can be moved over to the other side, where it becomes a left action on B prime. This tensor product of bimodules extends to complexes. So, given complexes of bimodules, so let's say we have one complex of bimodules that's like B. I have too many subscripts, too many B's. Let me call them M for now. So I have a M, let's say, complex of bimodules MK, MK plus 1, and so on, dot, 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 with some differential. And then a complex of bimodules N with some differential. Then you can tensor them together. And this is the complex defined to be, this is defined as follows. Maybe this is, should I define this? Do you guys, I'm sorry. I never know like how much background I should include.
Yeah, for me what you wrote on this blackboard is not very intuitive, especially these B with double R's and so on. I think I can grasp more or less what you mean, but...
See, the trouble is, spending too much time on this explanation is counterproductive because this falls in the...
No, I can trust that we won't use it.
Yeah, it falls in the aspect of things that are maybe technical, but not they're important for understanding the definition, but not the actual tool for computing that we will actually use. So let me just assert that there is a kind of multiplication operation on bimodules, and there's a multiplication, and it extends to a multiplication operation on complexes of bimodules. So now that I have defined a pair of, this is a complex, these are both complexes of bimodules, depending on the index I, we can then tensor them together, we can multiply them together to get a whole wide variety of complexes, depending on sequences. And the theorem that I wanted to state is that those...
Please,
Sorry?
wait a moment, I need to make a photo.
Oh, I'm sorry.
Maybe now it's... Yeah, because you know the quality of the video is not perfect.
Sure, sure.
And I plan to add also an album of photos of blackbirds. And you know, if you erase the blackbirds in alternating way, the framework is fine.
Of course.
I'm sorry, I should have told you about it. I forgot.
Just this left, but was inefficient use of board to begin with, so
Okay, now it's perfect. And you can go to the left, or if you want to keep it, let me just make a photo of the right one, and you can erase it.
I think I will keep the definitions, but then erase.
Okay, so let me just make a photo. Okay, yeah, you can erase.
Okay.
Now you can erase everything you want.
I'm sorry for messing up your pictures. So the theorem, which relates these things to, I guess, knot theory, is the following. So this is actually, these are called Rouquier complexes. These things and their tensor products are called Rouquier complexes. This theorem was proved by Rouquier in around 2005. These complexes satisfy braid relations. Excuse me. So first off, the thing that I'm calling Fi inverse really is the inverse to Fi. So there's an equivalence relation on complexes called homotopy equivalence. And this complex is homotopy equivalent to this complex. So R, just the identity bimodule by itself, we will regard as being a complex with zero differential, just sitting inside homological degree 0. So that's the identity bimodule, because tensoring with it doesn't do anything. And this relation is saying that the Fi and Fi inverse are really inverses. They're two-sided inverses. I should write the other one as well. So that's somehow the first relation. The second relation says that, so this is what's frequently just called the braid relation. And out of laziness, I'm gonna start dropping the tensor product symbol. So the tensor product, or the monoidal operation on complexes, is just going to be written by placing them side by side. So I'll be easy here. So the braid relation states that this product of complexes is homotopy equivalent to this product of complexes. And if J is not I or I plus 1, or, sorry, let me just say if J is far away from I, then those complexes commute. And so you should, each one of these relations should be visualized as corresponding to some relation in the braid group. So for example, the first one is just saying that braid generator and the negative braid generator are inverses, this relation is saying so you cross strands I and I plus 1, and then you cross strands I plus 1 and I plus 2, and then you cross strands I and I plus 1. Well, that's equal to first doing I plus 1, and then doing I, and then doing I plus 1.
I have a question.
Yes.
Because in F, we map BI to R with some shifts.
Yes.
And in my simplified intuition, like BI is something with 2 copies and R is something with 1 copy. And you say that I should see it as a crossing in a braid.
Mm-hmm.
And crossing is something, that maps 2 into 2. And I have some.
What do you mean when you say 2 into?
So in BI there is R close R tensor R.
Okay.
And I would expect something like something tensor something mapped into something tensor something when I see crossing. And here it is not, and I'm very open to it, but I would like to see how to see the crossing in Fi in this definition.
Yeah. Okay. No, this is a really excellent question. What does this have to do with crossings at all? So let me. Okay. Yeah. This is a question that deserves an answer. So, okay. So let's talk about this for a second. So I'm gonna assign bimodules to pictures, and we're just gonna say for now n is just 2, because all of the interesting features will be present for just n equals 2. Okay, and so we have. So this is the identity braid. We have 4 variables: x1, which lives here, x2, which lives here, x1 prime, which lives here, and x2 prime, which lives here.
Okay.
So we start with our ring, and then the relation that defines this bimodule is, well, x1 equals x1 prime, x2 equals x2 prime.
This already helps.
Okay. Here is another bimodule. Why not consider this bimodule? This is a perfectly good crossing, isn't it? How would you define this bimodule? Well, I would take the same generators. I have x's and x primes, and then I would mod out by the relation instead x1 is equal to x2 prime, and x2 is equal to x1 prime. So this is called the identity bimodule, and this is called the standard bimodule. And you asked about tensoring together. Well, tensoring just means stacking diagrams on top of each other. So let's take 2 of these guys and stack them on top of each other. Now I have 3 alphabets. I have, first I have 4 alphabets. I have x1, x1 prime, x1 double prime, and x1 triple prime. And then similarly for x2s. So if I want to stack them on top of each other, then what that means is I need to take 2 copies of each little bimodule. But then I want to I want to glue the sort of boundaries together. So I want to identify x1 prime with x1 double prime. and I want to identify x2 prime with x2 double prime. So in the end, the glued picture really only has, I will say, let's say three alphabets. x1, x2, x1 prime in the middle, x2 prime in the middle, and then the last one I'll just, slightly abusive, but we'll call it like this. So anyway, this picture, this is what I mean by tensor product. Tensoring is, the tensor product of bimodules is taking two copies and then identifying the variables that get glued. Okay. And this bimodule, so what are the relations defining this bimodule? Well, we have our x's, we have our x primes, we have our x double primes, and then lots of relations. The relations are like x1 equals x2 prime equals x1 double prime, x2 equals x1 prime equals x2 double prime. And you can kind of just think about it for a moment, and you see that these two bimodules are equal to each other. The prime variables, the one in the middles, can be eliminated using these relations. x2 prime can be eliminated, and x1 prime can be eliminated. And even when you do eliminate them, you still get the relation which is defining this bimodule. But you didn't ask about these. You asked about B's and the crossings. So how do you get these B's out of this picture? So this is where a little bit of like homological algebra in the kind of classical sense comes into play. So what's the relationship between this bimodule and this bimodule? I know that's a very open-ended question, but in some sense, think about it this way. Think about it in terms of arithmetic, like really categorified arithmetic, because that's sort of secretly what's happening here. So I'm claiming that this guy is in some sense associated to a crossing. This one, being the identity bimodule, is associated to the identity braid. And this thing being in the middle is in some sense like the difference between those two. Remember how I said like a complex categorifies its Euler characteristic. So this complex is in some sense is going to categorify the difference between these bimodules. So you should imagine a linear relation that looks like crossing, at least decategorified crossing equals whatever this is minus the identity. Okay? And the relation is as follows. So the heart of what's going on here, the heart of like the answer to your question, Fyodor, is the following. So the claim is that we can identify let me be a little bit vague here and just say the bimodule that is associated to this picture we can identify this as a sub-bimodule of the identity bimodule, and then with quotient wait, is this right? Sorry. Remember how I said I should be thought of as associated to this little picture. So this dude, it could be thought of as a sub-bimodule of this one with quotient this. So the homological algebra way of saying this is that there's a short exact sequence. Now, I don't know if this phrase is part of the language or if it's it sounds scary or fancy, but a different way of saying exactly the same information is that there's a short exact sequence. This bimodule has a map, and in fact an inclusion, an injective map into this bimodule. And then the quotient is this bimodule. So in a certain sense, this one is built up out of two copies of these two. And what this complex does is it subtracts off the identity one, leaving only the crossing. There's a second short exact sequence. In which this guy includes as the sub. And the quotient is this guy. So, and then the point is that this map in both cases is exactly the component of the differential. So when you form okay, let me I'll talk about this as long as you guys like want.
For me, it's enough.
But yeah, so the point is that the formation of the complex Fi. So being a short exact sequence is analogous to saying that is like, so being a short exact sequence is just a three-term chain complex. So guy maps to guy maps to guy, and then, but whose homology is 0. So there's no homology here or here or here. So this complex should be thought of as like the 0 complex. So in the growth in D group of like the derived okay, I'm sorry, this is too many things. But very coarsely speaking, this bimodule wants to be made up of, wants to be like equal to, quote unquote, the sum of this one and that one. And the formation of Fi subtracts off this, leaving us with something like that.
Okay.
And this short exact sequence gives us a different expression. The same bimodule is also, in a different way, the sum of this one and that one. And then Fi inverse, the formation of the Fi inverse is like subtracting off this copy of the identity, leaving us with that. And the important thing is that here we are working in, there's two different kinds of categories of complexes one could be working in. One is called the derived category and one is called the homotypic category. And in the derived category, these two guys would be considered equivalent. In the derived category, these would be considered equivalent because they are both. Okay? But in the homotypic category, they are different. They're like, so anyway, which is why you get interesting topological, which is why you get one of them as a, which is why you get the braid group relations and not the symmetric group relations. Okay, that was way longer than I had planned to talk about that, but I think it's a really great question, and it's a good exercise, by the way. Why is there this short exact sequence? Okay. And I'm probably,
Yeah, you're more or less out of time. Sorry for that.
wait, sorry, I was supposed to go from, oh yeah, I'm more or less out of time.
But you know, if you need 1 or 2 minutes, or maybe 5 minutes, we can go for it.
Let me, so let me just think for 1 second. So, okay, I think that's a pretty good place to stop. I think what I will do tomorrow is just so start with the I will maybe not since I'm apparently going a little bit slower than I intended.
You know, if you want, we can.
No. I want to ask. Should I talk about? Okay, so I think I would rather tell you the technique for computing things, and we'll just start with that tomorrow. So there's so this procedure, together with something called Hochschild homology of bimodules or cohomology of bimodules, is what's required to actually define the complexes. And let me black box that. Tomorrow I will start by telling you like what we actually need for computations.
Okay. Thank you. Questions? Maybe easier ones or shorter ones?
Yeah, sorry.
No, it's sorry from me.
Yeah, so I mean, here this construction like really depends on this braid, but can you like set yourself free from this braid closures, or define it for like links in some other form? Because I mean, from the point of view of topology, having this braid closure form is sometimes quite restrictive. So I was just wondering whether this is some I don't know, assumption that make life easier, or it's just the only construction that we have.
It's a huge problem, like an open problem, but also just a problem that we can only define. We can only define this for, or so. Yeah. So first off, great question. So we can define complexes for link diagrams, which are not braid closures, but we can also prove that they are not link invariants.
Oh, I see.
In order to have, so this is work of Michael Abel. Like a lot of people thought long and hard about this and weren't sure if we could prove invariance for like under the general Reidemeister moves, but then yeah, so the answer is negative. So the things that we know how to define, which don't depend on the braid closure, just like are defined for any link diagram, are not. So the offending Reidemeister move is this one. It's called Reidemeister 2b. So it's the Reidemeister 2, but where you see a loop. This is the sort of thing that you will never ever see in the braid-like Reidemeister moves. Because braid-like Reidemeister moves, well, we always orient our braids in a parallel fashion and not in an anti-parallel fashion. So this Reidemeister move is okay, but this one is not. And it's a huge problem to like write down a definition which doesn't utilize the fact that you have a braid closure. This is one of many reasons why Humphrey homology is quite strange.
Okay, so a follow-up question, if I may.
Yeah.
So what about functoriality? Because for braids there are these braid cobordisms.
Yeah.
So is this construction functorial?
There are braid cobordisms, so this is functorial under braid cobordisms, but it's a much more restricted class of cobordisms.
Okay.
Yeah, than just all cobordisms.
Yeah, but I mean, if you are not able to construct any type of invariant or any invariant of this sort for general link diagrams, then it's hard to expect to get like a full functoriality.
Yeah, that's right. I should say though that this Homfley homology is some kind of master homology theory. There's many homology theories that it sort of like specializes to. So there's SLN, Kovanov-Rorzensky homology, and possibly others. And these descendants are all functorial. Like the only really weird one is the Homfley homology, the one that sits at the top. But the specializations like Kovanov homology or the SLN Kovanov-Rorzensky homology are all functorial, and they don't require break closures.
Okay, thank you very much. I'll stop the recording and